All right, so in this example, we have an unknown compound, and so we are given a molecular formula. So I'm going to draw that a little bit bigger in case it's hard to see. So C4H9Cl. And what we have are different types of spectra that are all corresponding to the same molecule. So that's an important point to make, that we want to make sure when we propose a structure that what we have said is consistent for all of these different types of spectroscopy. And so there's no one correct way to approach this. I can make some recommendations about the things that I look at first, but really it's kind of a personal process of putting together the puzzle pieces. That being said, most of my students are much more comfortable solving structures or get more information, and me too, from the infrared spectrum and from the NMR spectra. So I like to look to the IR spectrum to get some obvious ideas about the functional group. So the signals that stand out to me here, I've got these signals, and again, it might be hard to read because it's kind of small. So 2986 to 2866. So these are just below 3,000. This looks like those sp3 carbon hydrogen stretches. And these other bonds that are indicated are below 1,500. These are in the fingerprint region, so we're not going to worry about those. I will tell you they're also associated with alkyl groups. So really all we're seeing from the IR spectrum is that we have sp3 hybridized carbon atoms. And that's not surprising if you look at your molecular formula. 9 hydrogens on 4 carbons, this is pretty saturated. So we don't expect to have any sort of pi bonds in here. And the next thing you might go to, or I would probably look at either the proton or the carbon, and which one I looked at first might depend upon the information I got from the IR. But if we look at the Proton Nmr, what we've got here is we have a 9 hydrogen singlet. Wow. So what that means is that all 9 hydrogens in our molecule are the same as each other. So there's really only one possibility for that. To have 9 hydrogens that are the same, it probably means that we have 3 CH3 groups. Okay? So they would have to be attached to the same atom, and if we're looking at our formula, that's going to account for 3 of our carbon atoms, so it's probably a central carbon atom that these are all attached to. Right, so those are our 3 identical CH3 groups. And if we take a look at this, now we've accounted for 1, 2, 3, 4 carbons and all 9 of our hydrogens. We're only missing one element at this point. There's only one thing this can be. We've got to have that chlorine attached to the carbon in the center there that doesn't have a full octet yet. So we're done. But let's make sure, remember again, that these are all corresponding to the same molecule. So all of this data should be consistent with our proposed structure. So let's take a look at the carbon NMR. We see that we have 2 signals, so let's call them A and B. And so this signal A at 67 ppm is a little bit high, right, for an sp3 hybridized carbon, which we know is what we have. And so this happens when you have your carbon attached to something that is electronegative. And we have a chlorine. So this piece of information appears to be consistent. So I would say that A, that carbon is this signal here. And then this signal at 34 ppm, we only have 2. That's indicative of a pretty symmetrical molecule, which is what we're seeing. So these carbons here should be B. Okay. And then finally, if we wanted to take a look at the mass spectrum, just to make sure we can at least explain, say, the major peaks. So we are given the molecular ion peak. So oftentimes when you're given the molecular ion peak, that's because it's not showing up. And that's not unusual for an alkyl halide. Their molecular ions are not particularly stable. So we're seeing fragments here, 77 and 79. So the difference between 92 and 77, this is the loss of a methyl group. So that's a loss of CH3 from your molecular ion. And so that makes sense. So we would expect, if we wanted to draw what that structure was for completeness, if we've lost one of those methyl groups, we have a positive charge on that carbon. And so we have this fragment. So we've lost a methyl group. And so this would be an alpha cleavage. And this is common for any functional groups. We cleave alpha to them. And that's because then you can usually have resonance stabilization from that functional group. Okay, so we have that resonance stabilized. And then we're probably explaining more than we need to just to verify this structure, but for the practice, it's not a bad idea. This peak at 100 is the base peak. So 100 being the relative intensity, not the mass to charge ratio. The mass to charge ratio we get from the bottom here. So the M/Z value for that is 57. And you might also notice that this has lost that characteristic signature of chlorine. So what this is the loss of chlorine from that starting molecule. So your base peak is this fragment. I'm just gonna draw a line in between these so we can make sure we're not confusing them. And if you add that up, you know, it's a nice stable tertiary carbocation. We'd expect that, and that does weigh 57. So it seems like all of our information is consistent, and this is the most likely structure.